Today we're comparing two of the most important robotic-assisted surgery platforms in the world. Medtronic's Hugo RAS system and Intuitive Surgical's Vinci system. On the surface, they both do the same job. They enable minimally invasive surgery using robotic arms, controlled by a surgeon at a console. But under the hood, they are very different systems, designed with very different philosophies. This matters far more than marketing comparisons. As biomedical engineers, clinical engineers, or field service engineers, these design choices directly affect how systems are installed, how they fail, how they're repaired, and how much downtime a hospital experiences. Even clinicians feel these differences in setup time, room layout, and ergonomics. In this session, we're not ranking which system is better. Instead, we're focusing on understanding why Hugo looks the way it does, why the Vinci looks the way it does, and what that means in the real world. Think of this as an engineering lens on robotic surgery, not a sales pitch. By the end, you should be able to clearly explain the differences to a colleague, a manager, or even a hospital procurement team. Hugo and Vinci are frequently compared because they represent two generations of robotic surgery thinking. Vinci has been on the market for over 20 years and essentially defined what robotic-assisted surgery looks like today. Most surgeons trained in robotics started on Vinci, and many hospitals already have multiple systems installed. Hugo, on the other hand, is Medtronic's answer to modern operating room demands. It was designed later, with less legacy constraint and with direct feedback from hospitals that wanted flexibility, modularity, and scalability. For engineers, this comparison comes up during site planning, tender evaluations, and long-term service strategy. Understanding both platforms allows you to speak confidently when a theater manager asks why Hugo needs 4 arm carts, or when procurement asks why service models differ so much. This is less about brand loyalty and more about understanding engineering trade-offs. One of the most fundamental differences between Hugo and Vinci is system architecture. Hugo uses 4 independent arm carts that are positioned individually around the patient. Each cart has its own robotic arm, power, and data connection. This modular approach allows flexible positioning depending on procedure type and patient anatomy. Vinci typically uses a single patient cart with multiple robotic arms mounted to a central structure. This creates a fixed geometry around the patient. Once docked, the system behaves as a single mechanical unit. From an engineering perspective, architecture drives everything else. Modular systems can isolate faults more easily, but may increase setup complexity. Centralized systems can be quicker to deploy once mastered, but faults can affect the entire platform. Neither approach is wrong, they simply optimize for different priorities. Both Hugo and Vinci place a surgeon at a console away from the sterile field, but the experience is quite different. Vinci uses a highly immersive console where the surgeon's head is positioned inside the viewer, blocking out much of the external environment. This can improve focus, but creates a physically enclosed experience. Hugo's surgeon console is more open in design. The surgeon still uses 3D visualization, but the physical layout feels less enclosed. From a service perspective, this matters more than you might expect. Console accessibility, transport, and ergonomics all influence maintenance time and failure recovery. Engineers often underestimate how frequently consoles are moved, adjusted, or transported. Design choices here affect cable strain, connector wear, and long-term reliability. Hugo's robotic arms exist as independent units, each mounted on its own cart. Each arm has its own drive systems and interfaces. This allows arms to be repositioned or even removed from service independently. The Vinci arms are integrated into the patient cart. This creates a mechanically unified system that behaves very predictably once stopped. Instrument life cycles also differ between platforms, with each manufacturer defining usage counts, reprocessing workflows, and replacement thresholds. For engineers, this affects everything from spare holding to PM scheduling. Understanding arm and instrument design helps you anticipate wear points, error patterns, and common failure modes. Hugo's system tower is a computational heart of the platform. It houses system computers, video processing, network interfaces, and integration with devices such as electrosurgical generators. Power backup. Systems allow controlled shutdown during brief outages. Da Vinci also centralizes computing but follows a different internal architecture shaped by earlier generations of hardware. For engineers, knowing where intelligence lives is critical. When a system faults, the question is always whether the issue is local, distributed, or systemic. Tower-based architecture simplifies software updates and diagnostics but require careful thermal and power management. These are not abstract concerns, they show up as real service calls. Installation and daily workflow are where design philosophy becomes visible to staff. Hugo's modular arm carts allow flexible OR layouts, which is attractive to hospitals with shared theaters or space constraints. However, flexibility often comes with a learning curve. Da Vinci's fixed geometry is highly repeatable. Once teams are trained, setup can be extremely efficient. This predictability has value, especially in high throughput centers. Engineers are often involved in room planning, cable routing, and staff training. Understanding workflow impact helps you design safer installations and reduce user error-related faults. Hugo was designed with modern serviceability in mind. Modular FRUs, guided diagnostics, and clear subsystem boundaries aim to reduce downtime and simplify repairs. For field engineers, this often translates to faster fault isolation. Da Vinci benefits from a very mature service ecosystem. Processes are well established, training pipelines are proven, and failure modes are well understood after years in the field. From an engineering career perspective, both systems offer learning opportunities. Hugo exposes you to newer design philosophies, while Da Vinci teaches you how large-scale deployed systems evolve over time. Cost discussions often focus on purchase price, but ownership is far more complex. Hugo's modular design allows phased investment. Hospitals may add capability over time rather than committing everything upfront. Da Vinci often represents a larger initial investment, but offers predictability through established contracts and known utilization patterns. Engineers supporting procurement teams should understand how service contracts, instrument usage, and upgrade cycles influence total cost of ownership. This is where technical insight adds real strategic value. To wrap up, Hugo and Da Vinci are not simply competitors. They are expressions of different engineering priorities. Hugo emphasizes modularity, flexibility, and serviceability. Da Vinci builds on an integrated, proven design refined over decades. Neither approach is universally superior. What matters is matching system design to hospital needs, staff experience, and long-term strategy. As biomedical and service engineers, your role is not just to fix equipment, but to understand it deeply enough to support safe surgery, maximize uptime, and guide informed decisions. The understanding is what separates a technician from a true medical device engineer.